Hi there, I'm Ryan, an mlpack maintainer. In this video, I want to go from nothing to a simple working C++ data science project. This is a demonstration of how you might develop a solution with mlpack. You can follow along on your system as I implement the code. The only thing you need is for mlpack to already be installed on your system. You can see the video about mlpack installation for more details. Alright, let's get started by finding a problem to solve. Okay, so the task I want to solve today is classification on the forest cover type dataset. And so I've pulled up a website where you can download the dataset here. But first, let's just take a little bit of a look at the data. So the dataset is a reasonably large. Once we download it and uncompress it, it's like 600,000 points. And there are, I think, 54 dimensions. So in the description here, we can see what those dimensions are. So we have a bunch of features that are things about land. So what is the elevation of the land? What is the slope of the land? What is the percentage of hill shade? These kinds of things. And our task is to predict the cover type, or the type of the forest that covers this particular land. So there are a bunch of numeric features, and then there are a bunch, 44 specifically, binary features of, is it a wilderness area? What is the soil type? These kinds of things. So we want to use all of this stuff to predict the cover type. So I can go back and I can download the data here by just clicking here, and I'll download the data, and then we'll take a look at it. Okay, so I've downloaded the file, and it came to us as a gzipped file, so let's unzip it. And let's just take a look at the first line in the file. And so the file is a CSV, and so we've got all those features that we talked about, and then the last one is the label, which is the actual forest cover type. So this point has label 5. If we were to take a look at like the first 3 points, the first one is label 5, the second is label 5 also, third point is label 2. So we want to load this data into an mlpack program, use mlpack to split into a training set and a test set, and then use some classifier, and then see how we did in the test set. So pretty simple data science workflow. First question, how do we load data in mlpack? So I've opened up the mlpack website here, mlpack.org, and I can just click on documentation. And over on the left, when I look at the sidebar, I can see there's a page about loading and saving. That is exactly what we need. A load function. I guess we'll maybe get to save later, but for now we just need to load. So there are a handful of types of data that we can load. We can load numeric data, categorical data, image data, mlpack objects. In this case, I'm going to load it as numeric data. Now we do have binary features that you could call categorical features, but just for simplicity, let's do numeric data. So I'll click on this, and here is our load function. So first we need a file name. It's pretty straightforward, but the format is auto-detected based on the file extension. So our file is a CSV, but the file is .data. So let's change that to a CSV real quick. Okay, pretty easy. Move covtype.data, covtype.csv. Great. Back to our documentation then. The only other thing to note here is that matrix is going to be some sort of armadillo matrix object. So here we'll just use armamat, which is the 64-bit floating point matrix, the default. All right, let's write some code. Okay, vim workflow.cpp, that's what I'll call my file. And let's just write the basic outline of the file. So I'll include mlpack. For convenience, I'll import everything from the mlpack namespace, and then we'll have our actual program here. So the first thing we'll do, we'll load the data set from disk, and then once that's done afterwards, I guess we'll fill in the code to do that in a minute. After that, we'll split the data set into a training set and a test set, and then after that, we will train a model. That'll be exciting. Then evaluate the performance of the model on the test set. Okay, so that's what we'll be doing as we put the program together, but for now we're just loading the data. So let's create an armadillo matrix object called dataset. That'll be what holds the dataset, and then we'll just use data load. No, wait, the file name comes first. Type.csv dataset. And then that third parameter, fatal, we'll set it to true, so that if there is a load failure, the program will throw an exception. Okay, so that's the first part. Now let's actually take a little bit of a diversion and jump to the end, so to speak. So I actually want to now pick, so we're doing classification. Let's pick an algorithm. I'm going to pick the random forest. Let's pick that. So random forest is a class, and what I want to know is, what does random forest expect? What do we need to give into random forest? I'm going to scroll down. I'm going to skip the little example here, and I'm going to go to the constructors. So there's one that initializes without training, and there's one that trains on numerical only data, which is what we have. So we want data, labels, the number of classes, and then a couple of hyperparameters. So looking more closely at the parameters here, data is going to be an armadillo matrix. Cool, we've got one of those, but that has labels in it already, and the random forest needs the labels as a row on their own. And then on top of that, the labels need to be between 0 and the number of classes minus 1. But when I take a look, if I flip tabs here, back to our description of the cover type data, the labels, this cover type, is actually the range from 1 to 7. But 0 num classes minus 1, that would be 0 and 6. So our labels are 1 too many. So before we split the data, let's actually go back and split the data set itself into just the data and then just the labels, and let's adjust the labels so that they're between 0 and the number of classes minus 1. Back to our code, I'm going to add another little step here, which is strip the labels out of the data set into their own object and adjust them to have the range 0 to 6. So I'll create a row called labels, and this will just be the last row of the data set, because remember, with mlpack and armadillo matrices, data is column major, which means that each observation in our data set is a column, not a row. So compared to Python, we kind of need to think in a transposed way. Also, a thing to note is that data set is an armadillo matrix, but we're asking to get a row with type size t. So we actually have to convert it, which we can do with armadillo's conv2 function. So convert the thing to a row size t from, and the from is this data set row. Okay, so that gives us our labels, but we're not done yet because these are in the range 1 to 7. So we actually want to subtract 1. That is one way that we could do this here. Now, mlpack does have functionality to take an arbitrary set of labels, like 1, 10, 12, 15, or whatever, and then map that to 0 to the number of classes minus 1. But in our case, this is such a simple transformation, we'll just subtract 1, and that will work. And there's just one more piece, which is we still have the problem that the data set has the labels in it. So we can simply shed the last row off the data set. This will remove the labels from dataset. Onwards, back to the documentation. Now let's figure out how to take our dataset and labels and split them into a training set and a test set. So in the sidebar here, what I'm going to be looking for here is the pre-processing section. And now I mentioned just a second ago that mlpack does have functionality to turn arbitrary labels into the right range. You can click on the normalizing labels page to read more about that. But at this moment, I'm interested in dataset splitting. So, as expected, mlpack does provide a function that lets me split a data set into a training set and a test set, optionally with labels, which we have. So let's take a look at that. The function takes the data set, the labels, and then splits it into a training and test data set, and then training and test labels, and then I specify the factor of points that I want to use for the test set, and optionally whether or not I want to shuffle the data. But the answer is yes, I do want to shuffle the data. So let's apply that. Okay, so first, let's make objects for the training set and the test set. I'll also make armadillo objects for the training labels and the test labels. Okay, now that I have those, I can call data split with my data set, with my labels, and the training data, the test data, the training labels, and the test labels. And I'm going to hold out a factor of 0.2 or 20% for the test set here. So now, let's add a little bit here. Print the sizes of the training test sets. So I'll just print a cout. Training set has Train data at number of columns, points. Cool. And then we'll just print the test set. Test set has test data, points. Oops. There we go. Okay, cool. So now we'll get something nice on the screen. Next, it's time to train the model. So let's go back to the random forest documentation and figure out exactly what we need to pass. Okay, back to the random forest documentation. Scroll down to this constructor. This constructor we're interested in is this one right here. So here we'll pass the training data, we'll pass the training labels, the number of classes, which is 7 for the cover type data set. We need to specify the number of trees, the minimum leaf size. You know what, let's leave those as the default, because it's supposed to be a simple example. Let's just specify these 3. And this will not only create the random forest object, it will also train it. Okay, easy enough to write here. Let's create a random forest object called RF, and then we'll just pass the training data, training labels, and the number of classes, just 7. Just write down number of classes. Cool. All right, next, what do we do with it? We can train it. We did that. We want to classify with it. So what we want to do is we want to classify. I think what I'll do in this program, I'll classify on the training set and also on the test set, and then I'll compute the training accuracy and the test accuracy, and we'll print those to screen. And we'll call that a day for our workflow. So we have a classify function here, and it looks like we can predict on a single point. We could pass in 1 point, but actually I want to predict on the whole training set. So I want this version, where I'm going to pass in the data I want to classify, and then I'm also going to pass in, I scroll down here to see what predictions is. Predictions is a armadillo vector full of size t's that the class predictions will be stored into. So this is almost the output of the method. So pass in the data, the predictions will be filled. Back into the code, easy enough to implement. I'm actually going to change this. I wrote evaluate the performance of the model on the test set, but let's do it on the training set and the test set. So what we want to do is something like call rf.classify on the training data, and then we're also going to want to call rf.classify on the test data. And in order to do this, we're going to need to make some objects to store the predictions in. So we're going to create one called train predictions and test predictions, and these will just be vectors that after this function is run, we'll store the class predictions for those. Cool, so this will run classification on both of those. And the only thing remaining will be to compute the accuracy. So, training accuracy can be computed. Well, first let's take a look at this sub-expression. We can just compare the training predictions element-wise to the training labels. And that will give us a vector. And when that vector has elements that are 1, then we got the label right. When it has 0, we got the label wrong. So we can just accumulate the accu function, all of the elements in that vector, and this will give us the count of the number of elements we got right. And so we can turn that into an accuracy if we divide it by the number of labels that we have total. Now, these things are going to be size t's, not floating point numbers, so we actually need to cast one of them to a double so that we don't end up doing integer division by accident. We can do the same thing for the test data. Test predictions are equal to the test labels divided by a double casted version of the number of test labels. Cool, and then we just want to print it to the screen. So, training set accuracy. Train accuracy percent. Oh, wait, but the training that's going to be between 0 and 1. So we actually want to multiply by 100. Now it'll be a percentage. And then we'll print the test set accuracy. And that's all we want the program to do. So, just reviewing. First we load the dataset, but the dataset has the labels in it, and the labels aren't in the right range. So we strip them off the end of the dataset. We drop the row of labels. And then we use mlpack's functionality to split the dataset into a training set and a test set. And print the sizes of those just for fun. And then we train our model, just a one-liner, and then we classify the training set and the test set. Using those, we can compute the training accuracy and the test accuracy, and then we'll print both of them. So that is our workflow. Now, let's go ahead and compile it. So, save and quit. And compilation is pretty easy because I have mlpack already set up installed. I can just call my C++ compiler, and here I want optimization, so I'm going to specify -03 for the highest level optimizations. The program itself, I'll just call it workflow, and then the source file is workflow.cpp, and then we need to link against the Armadillo library. Okay, so now the program is compiling. This will take just a second or two. And when it's done, we can take a look at what we have. So we have the data, it's like 72 megabytes, and then we have the program, which is actually very small. It's like under 200K, so mlpack programs compile down to pretty much nothing. And then we have the source file itself. And now if we run the program, it should do exactly what we wanted it to do. So it'll load the data, split the data set. So you can see it's split the data set. We have 465K points in the training set. We held out about 115,000 for the test set. Now, the actual training process can take a minute, so I went ahead and skipped ahead to when it was finished. But you can see, based on the timestamps here, that it took about a minute to train all 20 of the trees in the random forest on all of that data. And the accuracy that we see, about 90% for the training set, which is pretty good, but really the number that matters is the test set accuracy. And there we got about 87%. So now a natural question is, well, are there other classifiers that do better? Well, let's find out. It turns out it's pretty easy to plug and play different classifiers inside of mlpack. So let's go back to the documentation. All right, let's pop open our list of classifiers and see what we've got. So we have a bunch of choices that we could use here. I'm going to kind of randomly select softmax regression, which is the multi-class extension of logistic regression. So if I take a look at the documentation, it's kind of structured the same. I have a constructor, and in fact, here's the constructor I'm looking for. It lets me specify data and labels and the number of classes and a couple of hyperparameters. So that's the same. And then once the model is trained, keep scrolling down, I can get to the classify section. I can see I have the same exact multi-point classification overload. Let's pass in some data, get back some predictions. Okay, that means we can just plug this right into our existing workflow. So let's open the file back up. And what I want to do, so since the APIs are the same, all I need to do is change the name of the class here. I can use softmax regression now. Now I'm going to be a little bit pedantic and say, well, RF isn't a good name. Now it should be SR. Maybe I should have just used the name classifier before, but I'm going to go ahead and change that. And I'm going to do one more thing too, which is just so we can be clear about the output that we're looking at here. Softmax regression classifier. Let's print that before we print the accuracies. Let's indent the accuracies a little bit. It'll be slightly more visually pleasing. Okay, so now that that's done, let's compile it again. And once it's done compiling, we'll go ahead and run it, and we'll see how it compares with the random forest. So run it. We'll load the data, and there, this didn't take very long, right? It only took 4 seconds to run the whole thing. Tell from the timestamps, but the accuracy of this classifier is really, really not very good. So it's possible, if I switch back to the documentation here, it's possible that if I go back to the training, there are a handful of options. I didn't go into the hyperparameters at all. Like maybe I need to specify a little more regularization. Maybe I need to specify a custom optimizer, like a custom gradient descent or something like this that will get better results for this data set. There are lots of options for what I can do there, but at least the out-of-the-box configuration of softmax regression, specifically on this cover type data set, is not doing very well. So it seems like we might be better off with the random forest. Now, one last thing I do want to talk about. So I'm going to go into the workflow. I'm going to change it back to use the random forest classifier again. So random forest. I'll change the name back to RF, and we'll be sure to fix this too. So when I compiled this, looking at this command, this will, by default, not use any of the OpenMP-based parallelism that's in either Armadillo or mlpack. So this will give us a single-threaded version. And so when I compile this and run it, I'll show you what I mean. So I need to open up a second terminal for that. Okay, made the font a little bit smaller on this one so that we can see a little bit better. Let's open up something that lets us monitor processes. And you can see I'm not running anything right now. The only things taking up CPU are my screen recording software. So if I switch back to this terminal and I'm going to run my workflow, because I compiled it without OpenMP support, you can see that the top thing here, workflow, is only using one core. So if we look at the loadout of all the cores up here at the top of the screen, only core 23 is being used. Well, that's not great. I have 24 cores. How can we use those? So let me Control-C this. We have to compile it just a little bit differently. The changes are pretty simple though. All we need to do is add the -f OpenMP flag. This will tell GCC, compile with OpenMP. I didn't do this originally because on some systems, OpenMP support might not be great. So if you're on Linux, you're good. OpenMP is generally there. If you are on OS X, it should be there. If you're on Windows, maybe your compiler supports it, maybe it doesn't. So, you know, you'll want to check and make sure that your compiler has OpenMP support. This may or may not work for you. It probably will. So now let's run this again, and I'll bring htop back into the picture. Okay, now I see something which is much more what I want to see. Our workflow is using all of our cores. And look, it took a lot less time also. So when I took a look at it before, it took like a minute and change, and some of that time was loading the data set. But when I look at the timestamps now, this now took like 34 seconds. So that's pretty good speed up. Okay, so that's all I wanted to show in this tutorial. A pretty basic data science workflow that, even though it was simple, hopefully you can see how you could expand upon that to go from some simple application to an actual complicated production pipeline with some machine learning and mlpack methods inside of it. If you have any questions, you can always consult the documentation. If you don't find an answer there, or if you find something that you think is a bug, feel free to open an issue on GitHub. I hope this video has been helpful to you, and thanks for watching.